Today I want to speak about the generative discriminative basis learning for medical imaging. Outline of my speech will be one introduction to dimension reduction, then I will go to the generative discriminative framework for extracting the feature of medical imaging. The part of this framework is general framework. Then I will go through each part of our problem that are the generative term, discriminative term, and priors. Then I will show you one image that it has a qualitative evaluation of this framework and end with the conclusion. The purpose of dimension reduction is to map the high dimension data into the lower dimension with preserving the main feature of the original data. Dimension reduction can be divided into two parts, two types of the reduction. First is the feature selection. It means we have some features and we decide to, for example, select some of them and ignore the rest. And one of the famous technique in this area is filtering. And the second part is the feature extraction. In the feature extraction, the data will, from the, for example, high dimension, will map to the lower dimension, which this lower dimension data can represent the original data. There is two types of the feature extraction techniques. First, generative, and second one, discriminative. In the generative dimension reduction, such as, for example, PCA, principal component analysis, or neural networks, the purpose is to, for example, find some lower dimension data that can preserve the features of the high dimension data. For example, here in this picture, this one is the neural network, can be used for example, dimension reduction. The input data is our original data, and the output also is the original data. And if we can train a neural network that's, for example, the input and output are the same, but the number of the hidden nodes in the middle is less than the number of the inputs, it's somehow it's a dimension reduction, because we have, for example, n number of the input and we have, for example, k number of the hidden node, and we can use the information of this k number to again reconstruct the original data, which is in the n dimension space. And for example, discriminative, something like linear discriminative analysis. For example, in PCA, we try to map the data into some bases that they shows the, for example, more information of the data. For example, here in this direction is the direction that, for example, PCA will choose to represent these two class of the data. But if we use for example, some features extraction, that's the purpose is to keep the data in the two different class. The LDA will choose this dimension, which can, for example, separate the data better than the PCA. In our problem, we have a set of input data. It's we call it X, and each X1 to Xn are the sample of the data that we extracted from the original data, reorder it as a column vector, and put it in the big matrix X. And we want to decompose the X matrix to two different matrices, B and C, which B is our basis that we want to have some properties that I will explain, and C is the coefficient, um, loading coefficient of each basis for each sample. And besides this decomposition, we want to have this form which with the some weighted vector, we can use the basis as some classifier that help us to, for example, label the new data. The properties of the B vectors, the most three important properties of the B vector will be: the first, we want to extract some feature, some basis vector that have some anatomic information of the body. It means, for example, it can be used for the next step in the for example, detection, maybe cancer detection or anything else. And we want to use these bases as a discriminators that can help us to classify our new data. And also we want to have these bases that preserve all of the data as much as possible, while maintaining their discriminatory abilities. For doing this work, I think I need to add one slide here. We, as I said here, we want to, for example, decompose this matrix X to two matrix B. B are our basis and C are the loading coefficient, which this type of the decomposition is famous, and there is some techniques that already use, for example, these techniques, but with different condition. For example, in singular value decomposition, we measure the difference between the, for example, decomposed matrices and the original data with the Fabius norm, and we have some constraint on the basis matrices, which is the B transpose multiple B must be identical, and also for the C. And it's based on what is our condition for example, the similarity between the composition and the original data, the assumption of the noise, I mean, and the constraint over each basis and the coefficient. We can find the methods that use this technique to solve the problem. In our problem, we assume the conditional independencies between variables xi, which are our inputs, yi our labels, b as a basis, c as a coefficient vector, and w for weighting matrix to use for classification. We formulate the problem as a maximum a posteriori estimation, map estimation, which we want to maximize the probability of B, C, and W given input data X and Y, and we can use the Bayes rule to expand this equation, and we can have the Pxy given Bc multiple probability of B, C, and W, and if I expand this equation, I will have this equation probability of P given Bc multiple P given Y multiple probability of Y given XBW, and probability of each of our matrices. And instead of finding the maximum of this function, we can use we can find the minimum of negative of this function, which here I use that, and I assume, for example, minus log of p x given bc is dx bc, and each term here is correspond to the, for example, one term. For example, this term is the correspond to generative term. The py given x bw is our discriminative term, and the log pb and log probability of b and the rest are our constant term. And for solving this problem, we must assume we must, for example, specify the each term in this optimization problem. We start with the generative term, and the generative term measures the divergence between original data and the BC, and based on the assumption of the noise between the original data and the decomposed metrics, we can define the generative term. For example, here we assume the Gaussian noise between x and BC, and we can use the Fabius norm between x, Fabius norm of x minus BC, and if we have a different type of the noise, for example, if it's Poisson noise, we can, for example, use the different generative term, which can be, for example, Kn divergence between x and bc. For in the second term, in our objective function, here was the, for example, discriminative term, and the discriminative term is to encourage to have discriminative basis which can used for the classification purposes. If we define a linear classifier like HWX, which is the inner product of W and V transpose X, we can define the loss function, which is the 1 minus Y, it's the label, and the value of the classifier. If this value is equal to 0, it means, for example, we have a correct classification, and if this one is not equal to 0, it shows our error to classification, and we define the for example, plus the positive part of this function as our loss function. And if we want to, for example, calculate the loss function for all of our samples, we can, for example, find the likelihood function, which is, for example, the summation of the loss function for each input, and do the summation over that, divide by the number of the samples. Yeah. And for the priors, in the objective function, we had, for example, 3 parts. First part was the generative that I explained. The second one was the discriminative, and the third one was the constant term. In the prior, we want to, for example, apply some constraint on the B, C, and W. Let's start from the W. We want to have the size of W as small as possible, because if the W is small, the margin of the classifier is big, and for example, because the W shows the direction of the linear classifier in the space, and if the norm of the W is smaller, we will have the bigger margin in the classifier. Yeah, I think I need again add one or two slides here. And for the C, we want to have the only positive loading coefficient, and we assume all of the coefficient in the C must be positive. And for B, we have two different constraints. First one we call it box sparsity, which means we want to have our basis function locally dense, and to shows the some to keep the to shows the information of each local part of the, for example, a big data. It will be help, for example, a person to it will be more interpretable for the person to, for example, match this type of the basis to the basis that describe to the part of the body which can describe which will be interpretable. And for this purpose, we assume there's a limitation for the number of the non-zero coefficient in each column of in each basis vector. For example, we assume there's a lambda that will control the number of the non-zero coefficient in basis vector, and also in the other side we want to use the basis function as a we have the basis function as discriminative as possible, which we want to have the value of bj, I mean, for example, each coefficient of the basis function be 0 or 1. And the intersection of these two sets will be our interest, and we can we can apply some relaxation on this problem, and instead of using 0 norm, we can use the 1 norm of each vector, and instead of having exact number, for example 0 or 1, we assume that, for example, the b can be between 0 and 1, and it means b must be bigger than 0, and the infinite norm of that must be less than 1. A second type of the prior that we want to apply on the B are the type of the prior. For example, if we have some segmentation, some segmentation on the data, we want to use this type of information to, for example, finding our bases. Because of this, we define two new norms, which is, for example, norm 1, 2 is equal to, for example, sigma of rho g of the norm 2 of the bj, in which bj be this line, g is the vector that, for example, for here, for example, g1, we use the original value of each point in 1, 2, 3, and 4 and put the 0 for the rest of them, and the norm defined by the, for example, number of the points in each set. For example, here is 4, here 2 and 3. It's 1 over, for example, the value, the number of the element in each, for example, segment of the data, multiple to the, for example, norm of each segment. And this constraint will help us to, for example, use some segmentation information of the, for example, some segmentation techniques to put into the, for example, our framework to find the basis that can, for example, have some or have some anatomical meaningful basis. And our optimization problem will have, for example, the generative term plus the discriminative term, and this norm of the W to have a big margin, and we can apply two type of the constraint on the B, which one of them is, for example, box sparsity, and the other is group sparsity. And as I said, we assume that all of the coefficient in C must be bigger than 0. And in the paper they assume the function that we must to optimize it is not convex in respect of, for example, all of the coefficient, but overall the variable. But if we, for example, we can have, for example, if we assume, for example, B is only the variable, the rest of the for example, B and W are fixed, we can, for example, solve this optimization problem. And for example, if we assume the B is the variable and C and W is fixed, we have, for example, J tree that I will explain it, and we can find B for each step and use this B for example, J2, and find the C and do the iteration to reach to the local minimum of this function. If we assume that, for example, the W is the only variable in the first term of, which is the, for example, the generative part, we don't have any variable, and it must be, it is a fixed, for example, it's a constant term, and we can, for example, ignore it and, for example, do the optimization on the loss function and the, for example, this term norm of W. If we assume the which C is the variable, the loss function and this W norm don't have C, and the only function that we have is values norm of the x minus BKC. And if we want, for example, to assume the B is the variable based on the, for example, assumption of the sparsity, which is box sparsity or group sparsity, we will have a different constraint on Bj, and there is some solver that can solve each part of, for example, J1, J2 and J3, and by using this algorithm we can do the we can try to solve each part and reach to the minimum of function. And in this slide, I want to show, for example, some result of this algorithm. In the first row, you can see the result of generative discriminative basis learning, which are matched to the, for example, part of the brain. This one is the result of the non-negative matrix factorization, and the last part is the SVD, singular value decomposition. As you can see here, for example, here we have this some big there is no, for example, locality in the, for example, bases here, and here the bases are too local, and but here it's by, for example, changing the lambda 1 and lambda 2, we reach to, for example, some somehow local and some global information. And if you have any question.